Galvanic cells.
We will describe galvanic cells, define the electromotive force, also describe the standard reduction potentials table, and using that table we will be able to conduct cell voltage calculations associated with galvanic cells, which after all are batteries. So the chemistry of galvanic cells, meaning batteries, is the chemistry of oxidation reduction reactions, in which of course electrons are transferred. So for example, as you see here, if I place in a solution of silver nitrate a copper wire, I'm sure you remember that you used the activity series to see if this would lead to a reaction. And in this case it does, because as we learned in the past, the copper is more active than silver in this case, and therefore the silver will be reduced whereas the copper will be oxidized. So let's now remember some of the important terminology used in redox reactions. Here's a good way of remembering. Leo says Ger. Well, Leo stands for lose electrons, oxidation. From the previous slide, copper went to copper 2, therefore it lost electrons and it was being oxidized. Also, the species that is oxidized is known as the reducing agent because it reduces the other species. In this case, it reduces silver, which is, as you can see now, Ger stands for gain electrons reduction, and silver here does gain electrons, and therefore because it gains electrons, this is the oxidizing agent. Now, if you run this reaction in the same vessel as shown in the previous slide, well, no useful work can be done because we are not harnessing the flow of electrons. But if I separate the reduction the reducing agent and the oxidizing agent in two separate vessels, then we can do some useful work. In other words, we can harness the electrons and have the electrons do something. So let's look at this particular reaction and let's break it up into half reactions. And so if we do that, we have oxidation taking place with copper and reduction taking place with iron 3, because iron 3 is going to iron 2, and in order to do that it has to gain an electron. In other words, every mole of iron 3 is gaining an electron in order to go to iron 2. So if we were to separate the oxidizing and reducing agents in two separate vessels, okay, here is what it would look like. On the left side, I have a metal bar of copper immersed in solution, and as soon as the reaction starts, the metal bar is going to of copper metal is going to become copper 2 ions. On the right side, what I have in solution is iron 3, and that would be going to iron 2. Now the left side of this galvanic cell, which is really a battery, is known as the anode. It is assigned a negative sign because it is the source of electrons. This is where oxidation is occurring. This is where the reducing agent is, because this is where copper, each metal of copper, atom of copper, loses its 2 electrons, and in doing so it supplies the electrons, which in this case are now going through a voltmeter. Now the voltmeter is just there to measure the flow of electrons. Of course, that's not really all that much of a very useful work, but let's assume the electrons were going through some kind of circuit that did something like a radio. Well, that would be, let's say, more useful work. But anyway, we have a voltmeter there just to measure that there is a flow of electrons, which then proceeds on to the other side of the galvanic cell, which we call the cathode, this has a positive sign by convention. This is where reduction is taking place. This is where the oxidizing agent is. And this is where, in this case, iron 3 is going to iron 2. Now, please notice that on the cathode side, in this case, the electrode, which is what you see as labeled graphite is, the electrode is just a probe that is immersed in a solution. In this case, the graphite is only carrying electrons. It's doing nothing else but just carrying electrons into solutions so the reduction can take place. Now, a way to easily remember that anode is associated with oxidation and cathode is associated with reduction is just to notice that the anode and oxidation start with vowels, and cathode and reduction start with consonants. Now, however, this galvanic cell is not finished yet, because notice that the moment on the anode side, the moment I start converting some of the metals, some of the copper metal atoms into copper 2 ions, in solution I'm going to have immediately a buildup of positive ions. On the other side, on the cathode side, the moment I convert each iron 3, okay, into an iron 2, I'm going to leave 1 moles. I'm going to create an extra. What I want to say, I'm going to create 1 mole of an ion that is not coupled with a positive charge. Meaning, let's assume that this is a solution of iron 3 nitrate. Every time I convert 1 mole of iron 3 to iron 2, I'm leaving I'm putting into solution 1 mole of nitrate ions that are not being matched electrically, okay, by a positive charge that was there before. So, in the cathode side, very quickly, I built up negative charges. This actually immediately stops the reaction from proceeding. So we need now what is called a salt bridge, which could be a gel, or let's say even cotton that has been impregnated with a solution of a salt whose ions are not in any way involved in the reaction. So something like potassium chloride would work very well in this case, or sodium nitrate would also work very well. And what does the salt do? Well, the potassium ions, the chloride ions are immediately pulled into solution on the anode side to counterbalance the copper 2 positive ion buildup. And on the cathode side, the potassium ions are being pulled into solution to counteract the buildup of the negative anions. Now, the galvanic cell will continue to work until we have essentially used up all the copper and all the iron 3 that is in solution. Well, here is another example of a galvanic cell. This is a zinc copper cell. Notice that on the anode side we have a metal borrowed zinc, in this case, that is in a solution of zinc sulfate, and then zinc is being oxidized to zinc 2, of course, and in doing so, the electrons that are released every time a zinc metal atom is converted to zinc 2 are moving through the wire, through the voltmeter, which then move on to an electrode made of copper, okay? And in this case, the copper, once again, is just a carrier of electrons, because what it's doing on the other side, where we have a solution of copper sulfate, is just a place where the copper 2 ions that are in solution are being reduced and depositing on the copper electrode. Now, once again, the salt bridge is in the middle, connecting the two beakers in this case, and providing the positive and negative ions to make sure that the reaction can continue. And so therefore the overall reaction is zinc that is being oxidized while the copper 2 is being reduced. You also have to be familiar with the line notation for describing galvanic cell. Let's just say that it is a shortcut, okay, to writing galvanic cells. So for the reaction we just looked at, assuming that the copper 2 and the zinc 2 are as standard conditions, in other words 1 molar solutions, you would describe the galvanic cell this way. On the left side, I start with the anode and I separate with a line from the species which is produced by the oxidation, and that species that is being produced into a solution of zinc sulfate, which is 1 molar solution. The species that is being reduced, and notice the two lines in the middle represent the salt bridge. The copper 2 is the species that is being reduced, and the concentration of the solution at the very beginning of the reaction was 1 molar, and the cathode is copper in this case. When I'm using inert electrodes, I would write it a little bit differently. So let's assume that this reaction, I have a reaction between zinc and hydrogen and acid. Okay. Well, the anode and this, the first part of the description is exactly the same as before, but if I have a species that is being reduced in solution and it remains in solution, I will write the species reduced. This is now on the right side of the description after the salt bridge. Okay, the species reduced, then the species being produced from the reduction, and then my line, and then the description of the inert cathode that I'm using, which in this case is platinum. Okay, let's apply what we have learned. Write an anode and cathode reactions and a line notation for the galvanic cell that utilizes this reaction. Come back when you're done after pausing the presentation. Well, the oxidation takes place at the anode. The reduction occurs at the cathode. Therefore, here's my line notation. And I happen to use, in this case, an inert electrode like platinum, but could use graphite, I could use stainless steel. Those are your typical inert electrodes. Let's start putting some numbers now on this process. We have to define now the electromotive force. What is it? Well, it is that electrical potential difference between the anode and cathode, which we refer to as EMF, electromotive force, or cell voltage, or cell potential, or E subscript cell. Or let's just say in the case of a battery you're probably familiar with, and 1.5 volt battery, the 1.5 volt would be the electromotive force. Now, for just about any reaction of this type, we can measure that potential difference, and we refer to this electromotive force, I mean the way we understand it, the way we describe it, it is a push-pull driving force in which the reducing agent is pushing electrons and the oxidizing agent is pulling electrons. Now the unit of electromotive force are volts. The symbol is V, is also and the volts are a combined unit composed of joules of work per 1 coulomb of charge. So 1 volt is equal to 1 joule of work per 1 coulomb of charge. Here is how we go about measuring cell potentials. So first of all, we have a reference cell which we call the SHE cell, the standard hydrogen electrode cell, in which we have a 1 molar solution of hydrochloric acid, and where the electrode in this case is a tube that has a platinum electrode inside it, and the tube has a outlet, as you can see here, where hydrogen gas can either be produced and it goes out the outlet, or hydrogen gas can come in through the outlet to go into solution. So when oxidation reduction occurs here, well, here's what happens when oxidation takes place. The hydrogen gas becomes hydrogen ion. In other words, the concentration of the hydrochloric acid begins to increase, and the pH, in other words, of that solution decreases. When a reduction reaction occurs in this cell, well, the hydrogen ion in solution is converted to hydrogen gas. We have assigned by convention the value, the voltage value, the cell value to this cell as 0, and we use this as a reference point against which we measure all the other cells, and out of this we're able to put together a table of electromotive force values, which we typically refer to as standard reduction potentials. Okay, let's see how we are able to determine the voltage value for a variety of cells. So we have hooked up a SHE cell to a copper cell, which is made up of a copper electrode and a solution of copper 2 ions. Well, in this case, as you can see from the voltmeter and the electron flow, because hydrogen is being converted to hydrogen ion, that the electrons are flowing to copper, which means that copper 2 ions are more easily reduced than hydrogen ions by a value of 0.340 volts as measured by the voltmeter. So the reduction half reaction, showing copper 2 moving to copper, has an electrical potential of 0.340 volts. Now we collect the voltage values for a variety of cells and into a table which we call the standard reduction potentials table. So notice that all the reactions, the half reactions written in this table, are reduction half reactions. We write it that way by convention so that we can tell that which species is more likely to be reduced. That would be indicated by positive larger voltage value, and which species is less likely to be reduced. Of course, that would be indicated by negative larger values. Now let's look. Let's also kind of do a little bit of ranking of the ability of this various species to be either oxidized or reduced. So in the case of fluorine, as you can see here on this list, fluorine is very likely, highly likely, to be reduced. This makes fluorine the strongest oxidizing agent on this list. On the other hand, the fluoride ion, okay, and of course I'm thinking if I were to go to reverse, if I had to reverse this reaction, the fluoride ion would be, in this case, the weakest reducing agent. In other words, the fluoride ion is not very likely to be oxidized. Okay, hope that makes sense. On the other hand, when I look at the half reaction at the bottom of the table, I can say that the lithium element is the strongest reducing agent because its ion, the lithium ion, is not very likely to be reduced given the large negative value that it has. So lithium is the strongest reducing agent in this case, and the lithium ion is the weakest oxidizing agent. A few pointers about the table. The cell values are written for reduction F reactions conducted at 1 molar concentration, 25 Celsius, and 1 atmosphere for gases. The more positive the cell value, the greater the tendency for the reduction reaction to occur, as already pointed out. F reaction also reversible. In other words, when I write the F reaction as an oxidation F reaction, the sign of the cell value is simply reversed. Very importantly, also, changing the stoichiometric coefficients of the F reaction does not change the cell value, because the cell value is an intensive property. Lastly, varying cell concentrations, temperature, or pressure for gases can affect the cell value, and this will be reflected in a calculation we'll be doing later using what is called the Nernst equation. Okay, so let's see if you can read the potentials table correctly. Order the following species, starting with the strongest oxidizer. Pause the presentation, go back to the table and see if you can do this. Come back when you're done. Okay, here are your answers. So the more positive the cell value, okay, the higher the oxidizing agent strength. So here's the order. Most to least likely to be reduced, okay, meaning highest positive cell value. And here it goes. Oxygen, nitrate ion, silver ion, and zinc ion. And here are the numbers to back up that list. As you can see, oxygen has the largest cell value. Okay, now rank these species. Pause the presentation, come back when you're done. Alright, let's see how you've done. So the higher the cell value for the reduction F reaction, the lower the reducing agent strength. In other words, the cell value and the reducing agent strengths are inversely proportional to each other. So the most likely to be oxidized is the one with the least positive value, cell value. And so here's the ranking, and here's are the numbers to back it up. Let's take a look at the activity series again. Okay. If you remember, in the series, a metal displaces from solution the ion of a metal that is below it in the list. So this really means that the metals that are above the other one are more easily oxidized. So essentially, the activity series lists metals in ascending order of their standard reduction potentials, with the strongest reducing agents at the top. And as a matter of fact, once you understand this relationship, now you can use the standard potential table that comes with the reference tables that are given with the AP exam. You really do not need an activity series, because that is the activity series. You can use the standard potential table as the activity series. Okay, so now that we have the potential values for a variety of cells, let's combine different cells and see what kind of voltage output we can get. The voltage output of a cell is given by the summation of the voltage value of the reduction reaction plus that of the oxidation reaction. So let's take a look at this reaction and see what kind of output of voltage we get. So first thing you do is look up the reduction potentials values in the table. And of course, they are written all as half reduction reactions, which I proceed to do, as you see here. And then I go and get the copper 2 reduction value, and I write the information here. Now, one of the reactions has to be reversed because one of the species is going to be oxidized. Now, which one is going to be oxidized? Well, the one that is least positive. And that is the case of zinc. So I take the zinc reduction half reaction, I flip it, and I change the sign of the voltage value. I rewrite the copper 2 the reduction half reaction as is, and now I add these reactions to come up with the desired overall reaction, and then I add the two cell values, and I come up with the fact that this reaction provides a voltage, this combination of two cells provides me with a voltage of 1.10 volts. Okay, often in this type of problems, you're asked to describe the galvanic cell fully. And when you're asked to do that, you're asked to do the following. Provide a balanced overall reaction, calculate the cell value, and indicate whether the reaction is spontaneous or not spontaneous. If the cell value is positive, then the reaction is spontaneous. If the cell value is negative, then the reaction is not spontaneous. I would have to put energy into it to make it happen. Then the last thing you need to do is draw the cell. You have to locate the half reactions in the correct locations, designate the anode and the cathode, indicate the signs of the anode and cathode, and also indicate the direction of the electrons and the ions flow in the salt bridge. On the other hand, when we hook up a zinc cell to the She cell, we notice that the electron flow moves the other way, meaning that the zinc is being oxidized in this case, and then the hydrogen ion in the She cell is being converted to hydrogen gas because it's being reduced. Okay, so this means that the zinc 2 ion is harder to reduce than hydrogen ion by a value of 0.763 volts. And because we write by convention all this reduction F reactions as a F reduction F reaction, even if the zinc is being oxidized, so we would write the zinc ion reduction as having a negative value of voltage, negative 0.763 volts. Okay, so let's describe this reaction completely. I mean the galvanic cell associated with this reaction completely. Now, from the potentials table, I have pulled out these two reactions. Of course, I've written them as reduction F reactions. So, which one is going to be reduced in this arrangement, and which one is going to be oxidized? Well, this one is definitely going to stay the way that it is, given that it is the larger positive value, whereas the other one is going to be oxidized, and therefore I flip it, change the sign of the value, and also, since I have to balance the electrons, I'm going to multiply top and bottom by integers that provide me with the equal number of electrons, because when I add them up, I want to make sure that all the electrons are gone. Now I'll go about calculating the cell value, and as you can see, it is simply 1.55. Let's now show a diagram of the galvanic cell associated with the reaction. First of all, here is the line notation for the galvanic cell. I have iron as my anode, iron 3 as the species produced from the oxidation. I have my two straight lines that represent the salt bridge, and on the cathode side in solution I have the permanganate ion going to manganese 2, and as a cathode I have an inert platinum electrode that is acting as my conduit for electrons to the cathode solution. So here are the species that are in the iron 3 is the species that gets created in the solution on the anode side, and so my iron anode has a negative sign. It is the cell, this part of the cell is where the oxidation is occurring, and iron is the reducing agent. The electrons are flowing towards the cathode. In solution, once again, I have the permanganate ion going to manganese 2. The cathode is inert. It could have been platinum, graphite, or stainless steel. Typically in lab situation we use graphite because it's lower cost. It has a positive sign. This is where reduction is occurring. This is where the oxidizing agent is. And of course I need a salt bridge to deliver ions to the 2 solution to neutralize those build-up of charges. Negative ions go to the anode, positive to the cathode, and here is the description of it. Okay, let's see if we can use the cell values to predict some reactions. Now in here we have silver that is being oxidized because it's going from 0 to +1, and sulfur is being reduced because it's going from 0 to -2. Well, let's see from the if we can use the values from the table to determine whether this reaction should occur as written. Well, since sulfur is being reduced, I leave the information I get from the table as is. On the other hand, I have to flip the silver reduction F reaction since as written in the equation it's being oxidized. Well, I add the voltage for these two reactions up, and I see that it's negative. Therefore, the reaction will not occur spontaneously as written unless I put some energy into the system, which I can do. This will be the topic of the next module, which deals with electrolytic cells. So, how should it be written so that it does occur? Well, obviously in the opposite sense, with the sulfide ion being oxidized and the silver ion being reduced. Now we add up both reactions and come up with the cell voltage value, which is positive, which says this is the way the reaction will. See if you can determine whether this reaction will occur as written. Pause the presentation, go to the tables, get the information you need, calculate it, and come back. Okay, from the tables, I was able to get this information. Obviously, as written, this reaction shows that iron 2 is being oxidized in order to go to a 3+ oxidation state. When I add the cell voltage values, I see that the reaction will not occur spontaneously as written. So in basic condition, a permanganate ion does not oxidize. Let's see if you now can check this reaction out to see if it will work as written. So come back when you're done after pausing the presentation. Well, here's the information I got from the table. I add them up, add everything up. Yes, this reaction will occur as written. The appendix has a lot of interesting information that I asked for you to peruse on your own. I will dedicate a few seconds to each slide, and if you're interested, of course, in that particular topic, then just go ahead and pause the presentation so you can take a look at the slide as long as you like. We have come now to the end of the presentation. Call me if you have any, or contact me if you have any questions.